Hello everyone, my name is Tehya Pavelka and I'm a mechanical engineering student minoring in math and bioengineering. My thesis director is Dr. Dominic Casadante and my second reader, who is also my supervisor and a great help on this project, is Akhu Gubalak. My thesis is titled Performance Enhancement of Polymeric Heart Valves by Varying Control Points of Fundamental Curves. I'm going to start with a little bit of background on why the research I have done is important. So cardiovascular diseases are the leading cause of death in the United States. There are a couple different classifications of heart diseases, but I'll be focusing on the valve-specific disease called aortic stenosis. AS occurs when the opening of the aortic valve narrows, usually due to calcification of the valve. This results in restricted blood flow from the left ventricle to the aorta, leading to a lot of different serious complications. Aortic stenosis is the most common of the valve diseases and is considered to be very serious. Cases caught early can be treated through medicine and lifestyle changes, but cases that are labeled severe require replacement of the aortic valve. There are three main types of replacement valves used in the medical field today. First are mechanical heart valves. These valves have existed for a long time and have a very simple geometry. However, because of the mechanical and chemical properties, patients are at an increased risk of blood damage due to shear stress. After surgery, patients with mechanical valves are put on lifelong anticoagulation treatments, which is expensive and burdensome. The second type of valve is known as a bioprosthetic valve. These valves much better match the geometry of a native valve and are made of tissues of other animals. These valves do not require the same treatment regime that mechanical valves do. However, their shortened longevity makes them a worse option for younger patients because of the risk of reoperation. The third type of replacement valve is called a polymeric heart valve, made of polymers as the name implies. Polymeric valves have acquired interest in recent research because of their potential to mimic the native heart valve's geometry, longevity, and mechanical behavior most accurately. The first step in developing artificial heart valves is computational simulation of the valve under physiological conditions. In order to do this, a geometry must be created in software such as an Autodesk Inventor. There are three curves that define the geometry of a leaflet in a valve: the belly curve, attachment curve, and free edge. The belly curve creates the round bottom of the leaflet, the attachment curve connects to the aorta or ringside, and these two curves are connected by the free edge, which is the top edge of the leaflet and is free to move during opening and closing. This combination of curves creates the leaflet, which is repeated 3 times to generate the valve. Each of these curves have points that define their structure, which are called the control points. For the simulations, I created 8 unique geometries by varying these control points. I also used a polymer proposed in literature that was proven to effectively match many different mechanical characteristics of native valves. This study focuses on the mechanical properties of the valves to evaluate performance since, I'm a mechanical engineering major. So these geometries are then used for finite element analysis, which is a computational method used to predict how a structure reacts to real-world forces, in this case pressure. Each of the 8 geometries was placed under transvalvular pressure for the amount of time 1 heartbeat takes. Within this pressure profile, the valve opens and closes like this. From this data, I analyzed the performance of the 8 different geometries by measuring the geometric orifice area and the coaptation area. The geometric orifice area is the area of the valve when it is open, and the coaptation area is essentially the measure of contact between the valves when it is closed. Based off these measurements, I basically just made a huge table that matches these results with which control points were used for the unique geometry. Using a statistical evaluation method called analysis of variance, or ANOVA, it can be determined how much of the fundamental curves contributed to the areas. This provides us with information about the significance of the control points and how we can further develop geometries to better perform using these parameters as evaluation factors. So in summary, my thesis was essentially an optimization study of artificial valve geometries for computational simulation. This will provide other researchers with important information about generating optimized geometries when developing new aortic valves to be used in replacement surgeries to treat heart disease. Thank you very much.